So hello friends, in this video we shall discuss single line to ground fault. Okay, in our unsymmetrical three-phase fault conditions, we have seen that three ways fault can take place. So one is we have seen line to ground fault, and the other one is line to line fault, and the third way is double line to ground fault. Okay, so in this video we are limiting our discussion to single line to ground fault, and this single line to ground fault is the most common type of fault in the three-phase system, where the percentage of occurrence of this three-phase in three-phase system, this line to ground fault occurrence is 60 to 75% times this line to ground fault will take place, where for line to line it will be 15 to it is 5 to 15%, whereas double line to ground is 15 to 25%. It is the percentage of occurrence of these faults. Okay, now in the single line to ground fault, to have the calculations of the fault current and the short circuit MVA, let us consider a unloaded synchronous generator or alternator. Okay, let us consider a unloaded alternator. Okay, so here I am taking the star connected alternator, okay, with the neutral impedance Zn, and it is grounded here. So the neutral is grounded through neutral impedance Zn, and we are having the phase voltage as ER, EY and EB, whereas the line currents here we are having, it is net current IR, IY and IB. Okay, so according to Fortescue theorem, we have seen that a n phasor can be resolved into n minus 1 phasor with one co-phasal quantity, right? Such that we will be having from a unsymmetrical three-phase fault conditions, the unsymmetrical three-phase fault currents can be resolved into three separate sets of balanced fault currents in the manner like positive sequence current, negative sequence current and zero sequence current. Okay, so here as we discuss the line to ground fault, so as the alternator is unloaded, that means before fault, okay, before fault I can consider the IR to be equal to 0. Similarly, IY will be equal to 0 and IB will be equal to 0, right? Again, you can see the voltages here, your VR, VY and VB at the terminals, okay, they will remain balanced before fault. Okay, now after fault, okay, now let me consider the IR phase, okay, R phase is, okay, let me consider this IR line current is shorted or grounded through a fault impedance ZF. Okay, let us consider this fault impedance ZF. Now you may consider this ZF or Zn according to the circumstances you are having. Okay, it may be solidly grounded simply. Here also you can ground it solidly, and here also you can ground it solidly. Okay, so when you ground them solidly, there is no presence of Zn or Zf here. Okay, but I am considering Zn and Zf so that we can have a broader outlook on the equations as well. Okay, so that means here after fault what we see, this IY, here the circuit is open and here IB is open. That means your IY will be equal to 0, again IB will be equal to 0, and your IR is not equal to 0. Okay, so let us consider here the fault current as IF. Okay, so your IR will be equal to IF. Okay, and you can see here, if I say the voltage at this point is VF, so your VF will be simply equal to IF into ZF, right? IF into ZF. Now after fault, this VR, VY and VB gets unbalanced again. Now in our last videos we have seen that the currents IR0, it's a positive zero sequence current in red phase. IR1 positive sequence current, this is IR2. So if you put them in matrix, so if we are having 1 by 3 times of, okay, 1 by 3 times of 1 1 1 1 alpha alpha square 1 alpha square alpha, or you can simply write it as A. Okay, let us write it as A. Okay, 1 A square 1 A square A, and here we are having IR, IY and IB. Okay, so this will be the other matrix. Okay, fine. Now in the fault condition, that is line to ground fault, okay, line to ground fault, here we can see IR sorry, that is IY is equal to 0 and IB is equal to 0. So you put this as 0 here, this as 0. Now after doing so, what we get is your IR naught will be equal to 1 by 3 times of IR. Okay, 1 by 3 times of IR. Again your IR1 will be equal to 1 by 3 times of 1 into IR, A into 0, A square into 0. That means here also you will get this IR1 will be equal to 1 by 3 IR. Okay, and similarly your IR2 will be equal to 1 by 3 times of 1 into IR, A square into 0, A into 0. So that means your IR2 is also equal to 1 by 3 times of IR. Okay, now you can see here your IR is equal to IF, right? That means you can put here this as IF. So from here your IF will be equal to 3 times of IR naught, right? 3 times of IR naught. So from here you can see that we have seen VF will be equal to IF is 3 times of IR naught into ZF. Okay, now as you can see here, the positive sequence current, the zero sequence current, the positive sequence current and the negative sequence currents are equal. That means they must be connected in series, right? So let us draw the equivalent circuit for this star connected load, which is line to ground. So while considering the per phase equivalent diagram, we know that the I neutral current will be equal to 3 times of IR naught, right? That means only the zero sequence current will be containing in the neutral current. Okay, so that means your neutral current contains only the zero sequence current, and this shows the absence of the positive sequence current and negative sequence current in the neutral. Okay, that means in the neutral the current flowing will be 3 times of IR naught. Okay, so if we start our equivalent diagram from here, from the neutral, so let me say this is your ground. Okay, now from here I am having a impedance, let me say this is Zn, and here the current flowing is 3 times of IR naught, right? Now going forward, okay, as there is no power in this circuit or no current flowing in this circuit, your EY cannot be considered, okay, and your EB also cannot be considered as they are open circuited. Okay, so here in the alternator we will be taking in a positive phase sequence, your ER is considered because it will be the rotor will be rotating in the anti-clockwise direction, and in that direction we will be considering the positive sequence EMF. Okay, so that means here we are having the positive sequence EMF, that is ER1. 1 is for positive phase sequence, and above we are having, okay, the sequence impedance in positive phase, that is Z1. Okay, and as the currents in the positive phase sequence, zero phase sequence and negative phase sequence are equal, they must be connected in series. So here we are having the impedance, respective impedance of positive, that is zero sequence phase, and negative sequence phase. Okay, so this will be like this. So this will be simply your Z2 and this will be Z0. Okay, so here the current will be your IR2. Okay, here the current will be IR0, here the current will be IR1, right? So you can easily find the voltages here. So your VR1 will be equal to ER1 minus IR1 into Z1. This is VR2, this is VR0. Okay, and again we are having here the ZF, and this is grounded here, right? So we know this. Now you can see that the current flowing here in the equivalent circuit is, finally we are having IR0. Okay, but here from the ground you can see the current here, it is 3 times IR0. That means in order to make this current and this current equal, what we do here is I will multiply this Zn 3 times. Okay, so that you will be having the current simply as IR0, right? Okay, so in our last videos we have seen that, so if you multiply this neutral impedance with 3 times, then the current IR0 can be written here. Now again you can see here the current here, it is IR0, right? Okay, but here you can see your IF is given as 3 times of IR0, 3 times of IR0. Now in order to make this 3 times of IR0 to be equivalent to IR0, what we do it is we multiply the fault impedance again 3 times of ZF. Okay, 3 times of ZF. That means we are shifting this 3 to ZF, and I am writing this simply as IR0 into 3 times of ZF, so that your neutral your fault impedance is multiplied thrice to the initial fault impedance, and to make the currents equal, so that we are having here IR0 and here also IR0, so that your new impedances will be changing, that is 3 times is multiplied for both the neutral impedance and the fault impedance. Okay, so this is basically the equivalent circuit diagram. Now by using this equivalent circuit diagram you can find the fault currents and the short circuit MVA. Now this can be found in many ways, so let us consider few ways here. Okay, so your initially if I say your zero sequence current, okay, your zero sequence current IR0 will be simply given by, what is the voltage here we are having, ER1. Okay, so it will be simply ER1, okay, upon the total impedances. So this is a per phase diagram, please remember it is a per phase, that means you will be having the per unit value only here. So it will be ER1 upon the impedances we are having Z0 plus Z1 plus Z2 plus 3 times of Zn plus 3 times of Zf. Okay, 3 times of Zf. So this is the equivalent impedance, sequence impedance for positive phase sequence, this is for negative phase sequence, and Z0 plus 3Zn is for neutral sequence impedance, and this is your fault impedance. Okay, so this is your IR0. Now we know that IF is simply given by 3 times of IR0. Okay, so what we do here it is, you just multiply 3 times of this term here, so that you got the fault current, and please remember this is in per unit. Okay, this is in per unit. Now when a value is given in per unit, how will you find the actual value? So your actual value can be found simply by, if I write here, your IF actual or in amperes will be given by IF in per unit into MVA upon, okay, MVA upon root 3 times of line voltage. Okay, so once you find the IF per unit value, okay, you can find the IF actual value by knowing the MVA of the system given and the line voltage. Now if we see the short circuit MVA, let me rub the board. Okay, so here one thing I must say is, so here you can see the fault current is going through a fault impedance ZF, and the neutral current is going through a neutral impedance Zn. Now if you connect it solidly to the earth, that means if I bypass this neutral impedance and connect to the ground directly, then your Zn will be equal to 0. Okay, your Zn will be equal to 0, and here also you can directly connect it to ground solidly, so that you can say solidly grounded, you can make this ZF to be equal to 0. That means you will be having the impedances, that is Z0, Z1 and Z2. Okay, when you connect the fault to the ground directly, and when you connect the neutral to the ground directly. Okay, by considering Zn and Zf, you will be having 3 times of Zn and 3 times of Zf. Okay, If you consider them to be solidly grounded, then they will be shorted so that Zn will be equal to 0 and Zf will be equal to 0. Okay. Now if in case the neutral is not grounded, if in case the neutral is not grounded, that means this circuit will remain open. Okay, this circuit will remain open and no current will be flowing. Okay, so that is ungrounded. Now here, in order to find the short circuit MVA, we are having several methods. Okay, one is from this circuit you can see that as here it is open circuited, here it is open circuited, that means we do not have any use of this EY and EB. Okay, that means here the fault current must be found. This is the fault current, here it is IF, and for the MVA we need the voltage and the current here. Okay, the voltage and the current here. So the voltage is ER and the current is IR. Okay, now why do we find the short circuit MVA? Short circuit MVA is found to decide the rating of a circuit breaker, so that the circuit breaker must act to limit the fault current. Okay, otherwise the system damages will be severe. Okay, and your conductors may also burn and it may damage the equipments in the power system. Okay, now the short circuit MVA can be simply written as, okay, so this is in actual values here we are considering, so it will be simply ER in volts into IR in amperes. Now your IR will be nothing but equal to IF. Okay, IF. So this IF is here again actual, and we know that IF actual can be found in this by using this formula. Okay, IF actual is equal to IF per unit into MVA upon root 3 VL. Okay, so this is ER in volts, that is actual value, and ER is here, it is a phase voltage. Okay, it's a phase voltage, and IR is nothing but IF in amperes, that is actual value. So this is one method of finding the short circuit MVA, and the other method is by using the fault complex power circuit. Okay, so by considering a complex power in 3-phase circuit, okay, so short circuit MVA, by considering the 3-phase complex power circuit, we will be having 3 times of ER1 into IR1 conjugate, that is a complex power, plus ER2 into IR2 conjugate, plus, okay, ER0 into IR0 conjugate. So this is a complex power, okay, of 3-phase circuit. This is 3-phase, that is why we are considering here 3. Okay, now you can see as EY and EB are 0 here, and you know that in the alternator your ER2 and ER0, we do not have any induced EMF in negative phase and 0 phases. Okay, that means the rotor is rotating in only one direction, and in that direction only we are having the EMF, that is nothing but ER1, that is in the positive phase sequence. That means your ER2 will be equal to 0 and ER0 also will be equal to 0. So you are left with 3 times of, okay, ER1 into IR1 conjugate. Okay, IR1 conjugate. Okay, again this is for 3-phase circuit. Okay, and again this is actual value. Okay, actual value we will be writing in volts, ER volts, and IR1 will be again volts. Now IR1 can be simply found because you know that your IR0 will be equal to IR1 and this IR1 will be equal to IR2, right? So this is per unit value again. Please remember this is per unit. Now to find out the, sorry, this is amperes, right? So this is volt, this is amperes, actual values. In order to find IR1, you have to again convert the per unit value to actual value by using the same formula again. You just substitute here IR1 actual. Okay, IR1 actual will be equal to IR1 per unit into MVA upon root 3 VL, so that you can find here. Okay, now if you again like to find the short circuit MVA using this formula in per unit, so when you consider the per unit, this 3 will be removed because we are considering in per unit, only per phase is considered. So this is for 3 phase, right? So here what you do is ER1 into IR1. So I hope this is visible, or I will write somewhere. So if I write here, it will be simply ER1 into IR1. This is per unit value. Okay, per unit value of ER1 and IR1, that is short circuit MVA. Okay, now one more method you can see. So while studying the symmetrical short circuit fault conditions, we have seen that the short circuit MVA will be simply written as, that is why you can say the 3-phase short circuit MVA 3 times of V into, that is a normal system voltage, into ISC upon 1000. Okay, or if you I have written MVA now, so you can put like this other 1000. So if you will be writing in kVA, so it will be 3 times of VISC upon 1000. Okay, now I know that the short circuit current, so why we are considering this short circuit MVA which we use in the symmetrical circuit, because here also you are making your circuit to symmetrical circuits, right? Positive phase sequence, negative phase sequence, zero phase sequence, they are all symmetrical circuits. So you can employ this formula here as well. So what you do here, it is, I know that your ISC, that is short circuit current, will be simply given by I into 100 upon percentage X. Okay, 100 upon percentage X. Now what you do is you put it here, so that this will be 3 times of V into I into, okay, 100 upon 1000. Okay, this will be again percentage X, that is percentage reactance. So this can be written as the short circuit, sorry, let me say it can be written as base kVA into 100 upon percentage X. This is your short circuit kVA. Okay, now if you are writing this as MVA, then you can write short circuit MVA is equal to base MVA into 100 upon percentage X. Now for percentage X is nothing but your per unit reactance, right? Per unit reactance. Now you can find the per unit reactance using the circuit, just like simply your per unit reactance will be equal to Z0 plus Z1 plus Z2 plus 3 times of Zn plus 3 times of Zf. Okay, after finding this impedance, you can simply put it here. So base MVA is given for you in the question, and you can add this, or you can put this value in the place of percentage X, or you can make it as X equivalent and you remove this 100. Okay, so short circuit kVA or MVA will be equal to base kVA or base MVA upon X equivalent. So this is other way. So this is all about your single line to ground fault. I hope you have got what I taught in this class. Thank you.